Hello, everyone, and welcome to today's webinar. I'm Robin Carr, and I'll be your moderator for today's event. We're giving everyone just a moment to join. Thanks for being here. We'll get started in just a minute. For those of you that are just joining, we're giving everyone a moment to join. We'll get started in just a moment. All right, before we get started, I have a few housekeeping items to go over. If you lose audio or visuals, simply exit GoToWebinar and come back to reset your connection. The chat feature is available in your GoToWebinar menu panel and should only be used for general comments or requests for technical assistance. You can ask questions using the questions feature available in your GoToWebinar menu panel as you think of them. There is a handout for today's presentation. It's in the handout section of your GoToWebinar menu. If you'd like to get the presentation, it's important that you download that during this event, as it will not be available after the event. The presentation is being recorded and will be available on our Fluke YouTube channel within a few business days. We'll hear from our speaker, David Metz, and if there's time, we'll go into our Q&A session and we'll answer as many questions as we can. Don't worry, post those questions. If time does not permit answering here, I'll be sure to forward the questions to David for direct responses. As mentioned, our presenter today is David Metz. David is a sales application manager at Fluke for Proof Technic alignment products. He has been with Proof Technic for 7 years, and before that, he spent 31 years as a machinist at Exelon, working exclusively in power generation. Early years were in fossil and hydro units, then 6 years in their mobile turbine gang, working on all sizes and types of steam turbines. For the last half, as he was stationed at Limerick Nuclear Power Station and traveled to other stations for outage work, Peach Bottom, Oster Creek, 3 Mile Island, and even Hope Creek. David spent most of his time working as a millwright in the plant, working on equipment, and has a lot of experience performing alignments on all types of machines. His alignment expertise began by mastering dial indicator methods, then using Proof Technic laser tools, beginning with the original Optiline, then all of the newer models up to today's Rotaline. All right, you're here for the importance of precision shaft alignment. David, take it away.
Well, that covers my introduction. I was going to say all of that, but she got most of that in, and that's correct, and it covers my history as a mechanic and a person using alignment tools. My title at Exelon was a machinist, and like she said, I worked as a millwright, but I was trained as a machinist, so I have a lot of respect for the precision and the very small measurements that make alignment an art in a way. So I'm going to go through the PowerPoint that I put out today, and it's talking about the importance of precision alignment. Talk about a little bit about methods and modes and some of the other questions that arise when people talk about alignment. But hopefully you guys get something out of this. Like she said, there'll be questions at the end. I'll be glad to answer, and you can always get in touch with me later. So if you can, I guess, take my picture off the screen. So, okay, so the importance of precision shaft alignment, right? I'm gonna, I guess that's a picture of me, okay? That looks like the old days when you first started. Good old straight edge will get you going. We're gonna talk about what is shaft alignment first, right? So at the point of power transfer between two machines, right? So we have a motor and a pump, and typically there's a flexible coupling in between. But the definition of shaft alignment for today's reason is the point of power transfer from one shaft to another, the axis of rotation, meaning the center line of the rotation of both shafts should be collinear. And this is the important part. When the machine is running under normal operating conditions. Okay, that's the important part, because really we want to, people often quote, they say, why align a machine when it's fitted with a flexible coupling? And it is true that couplings are flexible and they can handle some mixed alignment, maybe 10 millimeter or more, but the load that is imposed on the shafts increases dramatically with any misalignment that's created, okay? And it's true that industry worldwide is losing billions of dollars a year due to misalignment. We're going to talk a little bit about the whys of that and how it costs you money in the end. But billions of dollars is probably not even an understatement. Okay, so rotating shafts must be aligned. Okay, whenever a machine generates vibration, the alignment must be checked. I love to show this picture. Okay, this is the reason we're here. This picture is a picture of two machines, one that is the one on the right, which is within tolerance and aligned properly, and the one on the left, which is out of tolerance. And it's just a heat picture, but it develops a lot of heat from all the pressures involved. Okay, you can see the coupling is heated up, but the real picture, the machine on the right is generating a lot of heat at the bearings. Now we put something together as a mechanic. We put a motor in place and we do a quick alignment and we fire it up and we run it, and we expect it to run 24/7, 365 days a year. And we'll put our hand on the motor and go, it's a little warm. But there's no real follow-up. There's no real measurement of how well we did. Just, it's a little warm, right? And in the case on the left, you can imagine with that heat generated, how long the grease is going to last in those bearings, okay? And then how long those bearings are going to last. So the goal is to put our stuff together and have it run as long as it is designed to run for. There's no way with an out of tolerance alignment, you're going to see the true life of the bearings in that machine. But this picture really does show it. It's clear. And this is a really old picture, but I show it every time I give a class, every time I talk about alignment. But the forces created in misalignment clearly are obvious when you look at a heat picture like this, okay? So when you have a misaligned machine, obviously a few things happen. Machine vibration is the first one that's obvious. You know, you'll have a vibe guy come out. As a mechanic, you're not typically the vibe guy. You might do the installation, maybe perform the alignment, and you walk away, and then the vibe guy comes around and he's going to take vibration measurements on your machine. He's going to see some vibration. So you get some vibration, right? Obviously bearings don't last. Might not be immediate, but bearings don't last as long when you have some misalignment. Coupling damage. Now, if you have one of those rubber couplings, or there are many different styles of couplings don't last very long with misalignment. But the one I like to talk about is seal wear. I was in a nuclear power plant where nobody likes radioactive material leaking all over the place. So when I first started, we used dial indicators for alignment, and performing alignments with a dial indicator is a bit of an art, and it's not really easy to be good at. But when we first incorporated a laser alignment tool into our mechanics toolboxes, we got an incredible amount of seal wear out of all of our machinery. So it was obvious that to us that seals were going to last longer if we did better alignments, right? So bearings, couplings, vibration, seal wear was a big one for us because, in the nuclear world, like I said, it's a big deal. But seals don't like to see vibration or force in any one direction because they're very, very, very complicated pieces of machinery, right? I can't be for sure to tell you where we got all these numbers, but I know our people have done a lot of studies in the past, and this is just one that was done, and they said that only 7% of all the machines measured, right, that fall within acceptable alignment tolerances. And I kind of believe that because I've done a lot of alignment measurements in the field, I want to say as found. So you go out to a plant and you put your alignment tool on there and you take measurements and you find out where it is. Very rarely when you do an alignment check is the machine in tolerance. And this might be right on the money, but 7% is a pretty low number for machines that are within tolerance. But to realize that, and you have a giant factory or a machine or power plant or whatever, if only 7% of your machines are in tolerance, you're definitely not at your optimum, okay? So we'll talk about the 4 parameters. I'm going to get you a little bit into alignment. I teach this class often, and I start right from the beginning. So don't be insulted if I'm talking about things you already know. But I'm going to talk about right from the get-go. I'm going to talk about the 4 things it takes to describe alignment. Okay, so there's vertical angularity, and when I'm in the classroom, I do this with my fingers. I just kind of turn my fingers up and down. But vertical angularity and vertical offset. Okay. Those are the measurable items. And then there's horizontal angularity and horizontal offset. Okay, so it takes those 4 things to describe misalignment. It's always a combination of all 4. I mean, rarely is anything perfect, right? But those are the 4 parameters of misalignment, okay? We're gonna talk about angularity first. That's pretty common sense when you see the picture here. The center line of rotation, okay? The angularity is the angle between 2 rotating axes. Axis spinning diameter, right in the middle is the angle. We give this angle as a gap, okay? We give it as a gap at a working diameter. We could easily give you an angle, 0.0 something degrees, but as a mechanic, it's really hard to turn degrees into what I need to do to make the correction. So if you give me an angle and it's in degrees and I have to move a motor, I don't know how far to move it, but it's in my brain. I can certainly understand when I have a gap at a certain diameter, and if it's in thousandths of an inch, I can measure that and move it and make the correction, right? So our tool defaults to a gap. You can certainly use an angle. I hear Europeans like to use angles. I don't know. I'm more of a gap guy. So we measure the gap at a certain diameter, okay? Realizing that if the different diameter coupling is going to give you a different gap number for the same angle. What we do typically is we just take a gap at 10 inches, and then I get a good idea what that gap is or what that angular number is. And then I get a better understanding of how well I'm doing, okay? So the angularity is done as a gap, okay? And the next thing that we need to look at is the offset. These are 2 different things, and this is really easy to understand in that top picture. The offset means the distance between the rotating axis at a given point. Now, when they're parallel, like in that top picture, this is really easy to understand. There's an offset. It might be, 10 thousandths offset between the 2, but the offset varies when an angle is induced. So it gets a little complicated to understand where the offset needs to be measured, because often with spacer coupling, you need it on one side or the other. Okay, but sometimes pictures like this can help. We care about the offset right in the middle where the coupling lives. Okay, we're going to talk a little bit about spacer couplings in a minute, but it'll become clearer why the number could be different on either side. So the alignment condition is always a combination of gap and offset, and this is a picture of what it really looks like. Okay, we got to correct those, but in this picture, it's kind of easy to understand. We have a coupling, and we have an offset in the middle of the coupling, and a gap that represents the angle. And we're here to fix those. As a mechanic, we're going to make those correct. The plus numbers and the minus numbers matter. Back in the day when we used the dial indicator, it was a big deal. Nowadays, if you use a laser and there's a results page, you get a nice picture, and it's obvious to anybody where you really are. So they've taken a little bit of the thinking out of it, but yeah, the pluses and the minuses do matter. Okay, so for a short flex coupling, and I'll show you one of those here. There's several different kinds. For a short flex coupling, which is a type of coupling where let's do this. The length of the flexible elements is less than the diameter of the coupling. Okay, we call that a short flex coupling, and that's what the tool defaults to. And these are several types of short flex couplings. All of these read their results in both gap and offset, and it's the simplest way to understand what your misalignment is. All of them act a little bit differently, by the way, and as an aligner, if I was teaching you how to perform alignments, I would get a lot into how much force these things shove into the process when you're measuring and trying to get alignments done. But typically, these are just short flex couplings, And there are many, many kinds. I don't even have all the brand names memorized. Some people throw names at you and say, well, we use this one or that one, but they're all a little different. They all act a little bit differently, but the results need to be shown in gap and offset, okay? And a short flex coupling is any one, even this one looks like a spacer coupling, we call it, but it looks like one, but the length between the two flexible elements is less than the diameter. Less than or equal to, okay? And we call that a short flex. The next coupling type I'm going to talk about just shortly is the spacer type coupling, where the flexible elements are further apart than the diameter of the coupling. This changes things because you have two different angles to deal with, and ignore the fact that these are weird numbers, but the results for a spacer coupling, as you can look in this picture, can show up different ways. First, they're going to show you in angles. The people who manufacture couplings often give you their tolerance, and they say, our coupling can handle this angle. Then they sell you the coupling. And as a mechanic, you go, well, what does that mean to me? And it's an awful thing for them to do. They need you to do the math. Nobody really wants to be that way. But typically when we do a spacer coupling, we read the results in two offsets. And the offsets are represented in the second picture up here. The offsets will give you the complete alignment picture, both vertically and horizontally, with just two numbers, an A and a B. Okay, don't ask me why they put the B first, but A, I guess, is closer to the motor, but it's A and B. It's always B and then A in the picture. You have two offsets, and it represents the misalignment condition. And if you look down at the bottom, you can see there's you can represent any misalignment with two offsets. You can see the pluses on one side or plus and a minus, and all those things will represent the results. Now this gets really confusing as an aligner because how do I turn that into something? The nice thing is, in the old days, we would have to use graph paper and draw a line and count the squares. It was an interesting proposition, but nowadays having a laser gives you a results page, and it has made it way easier for us, okay? So spacer couplings are a little bit different, okay? So that's kind of the basics for both reading results in alignment and, the two basic different types of couplings that we're gonna read results for, right? Next, I'm gonna get into how to recognize the symptoms of misalignment. This one should be a little bit obvious. If you have vibration, start there, put your hand on it, go, ow, it's vibrating really bad. Let's relook at the alignment on this machine. But if you have a machine that vibrates, if you have a machine that gives you premature bearings, seals, couplings, or shaft failures, and I say premature, when you put a machine together, it should last a pretty long time. I'm not going to give you the exact number. I know regular bearings are said to run for 1 million hours. I don't know the real number. Some do. But if it's premature, if you have a machine that's giving you trouble, you turn this machine on, every 6 months it breaks down. Every 8 months it runs down. Every 2 months. If you have a machine that's giving you trouble, premature failures, you should definitely look at alignment. Okay. Oil leakage at the bearing seals. Bearing seals are basically a lip seal to keep the oil into the housings. If you see a lot of movement at the shaft, obviously your seals are not going to last. Bearing and coupling temperatures. Now I showed you that picture of the temperatures. That's a pretty obvious thing to show misalignment, right? Cracking and breaking. Well, if you get into that, you're in a pretty bad problem. You definitely should look at it. Loose foundation bolts. Sure, you're getting some vibration to give you that. Interestingly, though, most people don't think about is energy consumption. Okay, you run a machine and it's eating up a lot of energy. You're gonna want to look at your alignment. We're gonna talk a little bit about that later. Okay. Direct and quantifiable costs. Well, we're not going to get into that, but so here's some consequences of misalignment. I love showing these pictures. I wish I had more. Nobody loves to see these kind of things. I kind of like it. I wish people would just send me all their failure pictures. If you have any, send them to me because I think it's fun. Misalignment does all these things. Where's your bearings out? Where's your couplings out? Okay. I'll show a few more later, but seals go bad, and all of these things cost money, right? If you own the plant or run the plant or you're in management, these are concerns. Okay. a picture of a typical pump to motor application. We use this one just to simplify what we're working on. I know there are hundreds of different configurations of things for you out there to be aligned, very large and very small. I've done alignments on main steam turbines where the generator is 450 tons, and we align that to within 0.02 of an inch. And you know, on the end of another machine might be a little tiny motor that's you can barely fit these heads on, and we line that up as well. We'll talk about some methods of alignment. Okay, originally, or at the base level, is the straight edge method. Okay, you put the motor next to the pump, you drop a straight edge on the coupling, and you eyeball it. We call that the straight edge. To step up from there, you would use a feeler gauge and measure between the couplings and get the feeler gauge readings in all four corners to be even. You can do a pretty accurate job at that, but this says that it's about as good as 5 mils, so 0.005 of an inch. You can see. Maybe when my eyeballs were good, I could see 0.005, but I'm getting a little old, and I got to wear cheaters, so I kind of doubt that's even that good. Then along comes the dial indicator method. Now, as a machinist, I had a whole box full of dial indicators, and I love them. Don't get rid of them because they measure in 1,000th of an inch, and they are very accurate. Okay. However, performing dial indicator alignment is not easy. It is not easy to be good at, and there are a lot of complications involved. You could see by that picture up at the top, there is some sag in the bracket that holds the dial indicator. Often mechanics, even good ones, will not remove the sag from the measurement. Okay, so having sag in your brackets is an issue. You're going to have it. You're going to think you're lined up, and you're not. So there are definitely issues with using a dial indicator. Things like loose brackets, reading the dials wrong. I could go on and on because I have a lot of experience using a dial indicator. Okay, and then along comes the laser shaft alignment. This must be a really old picture because that picture is a picture of the original Optoline back in the day. That's the one I learned on. I think it was 86 or 87, in the 80s, we learned how to use that tool, but it is very accurate. Okay, the laser reads in very small numbers. I think it's 0.05 mils. I think that's in microns. So it does read very accurately. Okay, so the laser did kind of took the sag out of the picture because the bars, the mounting brackets don't sag, and the accuracy level is really incredible. Okay. In order to do it, oh, I guess somebody put this in here. In order to do this with a straight edge, you got to be a wizard. In order to do it with a dial indicator, you need to be a specialist. It takes, I'm going to say it takes years to become really good at becoming a dial indicator aligner. Okay, and I was one. I've spent a lot of years using dial indicators. It is not easy to be good at. Okay, and with a laser, you can use a technician. Okay, any one of the people in your maintenance force can learn how to use a laser very effectively, measure the results, record the results, and give you really, really good alignment with just a short amount of time learning how to use it. Okay, so the dial gauge. Oh, I got dial gauge methods. I'm going to talk about this real quick. So there were two methods of dial gauge readings. One was rim and face, and you can tell by the picture on the left, the results give you a rim and a face reading, which is what we called them, but really they were offset and angle. Okay, so offset and gap readings you would take using rim and face. The reverse indicator method would be for the spacer coupling that we talked about, okay, and it gave you 2 offsets. Again, when you're doing the reverse indicator method, to get results, you need to use graph paper. Quite a complicated process, not easy to learn how to use, but along comes the laser, thank goodness. There are some benefits. It says there's a universal bracket, pretty darn useful for most machines, and we have some extra crazy brackets like thin, magnetic, and chain brackets, right? There is no bracket sag, and that's a big deal because if you know much about dials, when the brackets sag, you don't know it unless you measure the sag and add it into the equation. Okay, a lot of people don't. I love this next line here. It says human error free. I don't think so. Nothing is human error free, but it is closer to human error free. Okay. very accurate. Okay, like I said, we're in the 4 micron range. Okay, there's a nice graphical display of your results. You can see a picture of a motor and a picture of a pump and a little line that says this is the direction you are and this is by how far off. There's an evaluation of where you are, meaning this is your coupling results and this is what you need to do at your feet to make the corrections. There's a button to watch live corrections. So when you need to make the move, you just push the button and the laser watches the motor move. Hallelujah. When you use dials, it was a nightmare. But we have a live move, and the biggest one at the bottom is documented results. If you're not using a laser today, you're kind of in the Stone Ages. The nice thing about documented results is I can prove that I did the job. Okay. I used to get done a job and the machine would be vibrating and the engineer would say, "What did you do?" And I could show him the results. I did a great job. We're going to get more into why it wasn't a great job when we try to figure out where the machine lives while it's running. Okay. So here's our touch screen model, the laser alignment tool, and I'm going to try to explain why. There's 3 basic components. Ours uses 1 laser and 1 sensor. Okay, the laser shoots into the sensor, and I like to show this picture because this is why a single laser system is a great advantage. Okay, we have an extra large. This is our older model. That I don't have a picture of how the inside of the newer one works, but the newer one's even bigger sensor. But in order to figure out an angle measurement, we need two sensors to read the results. Because you look at Sherlock over there, he wouldn't know where the bullet came from if he only had 1 pane of glass, so you need 2. And if you have 2 panes of glass and you're trying to figure out an angle, the further apart the panes of glass are, the more accurate the reading. Okay, so what we do is we take the laser and we shoot it through the center of this sensor, and we have a sensor in the back that reads the laser. And then we have a piece of glass that reflects the laser off over to another sensor, and it's a little hard to see behind there, but there's a second sensor in there, and that piece of glass is curved so that the sensor acts like these 2 sensors are much further apart. I believe in our heads it's somewhere near, I don't know, I want to say 16 inches, but they act like they're around 16 inches apart, and the accuracy level for that is really incredible when we take the laser and the sensor and we put them right next to each other. Okay, so if I have a 2 laser system and I put 2 lasers right next to each other, they're going to act like this double pane of glass, and they're going to be really close to each other and not very accurate. Because we can take our sensor and shoot the laser into it right in front of it, and it splits the laser beam and magnifies with this curvature of this piece of glass, it magnifies the other sensor. We get a really, really accurate measurement for angles. Okay, so that's a really big deal. I didn't know this until I came here, but it's a really big deal because our tools are very, very accurate when the heads are right next to each other. Okay, so the system works. It's a really simple system to learn how to use. I'm not going to get too far into it today because I'm not really doing a demonstration of the tool. If you want to see one, please contact us and we'll give you a nice demonstration. But it works in a simple way. It's got, I want to say, 3 pages. Okay, there's a dimensions page where you just type in the dimensions. And there's a measure page where you just rotate the shafts and it does the measurement. And there's a results page, and on the results page, it's really nice because you can see that the motor feet corrections are displayed and the coupling results are displayed as well. So and then there's a live move button, which would be that red one there, and you would push the live move button, make the corrections, and perform the alignment. I'm not going to get too much into how to do it, but it's a really, really easy thing to learn how to use. Okay. As far as corrections go, you typically would use a shim to raise a motor. Typically, there are a lot of machines with a really crazy bolting sequences, and maybe some things have flanges on them, and there are other things, but typically we just put shims under it for the vertical, and we make a live correction sideways for the horizontal. Okay, there's a hammer with an X on it. I try to tell people not to use a hammer for other reasons, but the corrections are done live time in the tool, and you get to see what the corrections are, right? Now we're going to get a little deeper into the process. So I told you earlier that the definition of alignment includes collinear shafts at our normal operation speed and temperature, obviously, right? So if you run a machine and it doesn't live where it was when it was cold, our perfect alignment when it's cold is not really good. So our goal, our true goal, is to figure out where a machine runs when it's hot, or running, even if it has, you know, process pressures pushing the machine, or steam or water or temperature. All these things make a machine run, not where it was when it was cold. And the only time we can perform the alignment is when it's cold. We have to shut it off, wait till it's cold, go in and perform the alignment. Well, our goal is to try to figure out where this thing runs with thermal growth, or you know, whatever process that it does. We need to know where it runs so we have it lined up while it's running. So there's a couple ways we can do this. We can use the manufacturer's parameters, because a lot of manufacturers kind of know where their machines grow to when they're running full speed or full temperature. Like compressor manufacturers will often say, okay, set our compressor 10 thousandths low, because we know at full temperature it's going to run 10 thousandths higher than where it is. Okay, so manufacturers will often give you a thermal growth number. You can calculate these if you know the expansion of a material. So the material itself has a certain expansion number per degree, and our tool, believe it or not, has a calculator built in, and I'll show you that. The other way is to monitor the actual living position of the machines while they're running. And our top of the line model, the Rotoline Touch, allows you to mount the heads directly onto, and I think I have a picture, mount the heads directly onto it. Sorry about that. And watch it move. I'll get you a picture in a second. So there are different ways to try to figure out where the thermal growth is and where it lives. There are also different ways to handle that thermal growth. Easiest one is to deal with under the feet of the machine. So if we are making a thermal growth adjustment under the feet of a machine, we would just typically say, in this case, they're in millimeters, but in this case, they want it to be 0.04 and 0.07 low, so that when it heats up, it's going to grow that much. Okay. When we do it under the feet of the machine, we call it thermal growth. But as a steam turbine guy, we did it at the coupling. At the coupling, we call it a target value. Okay, so at the feet, we call it a thermal growth number. At the coupling, we call it a target number. So in steam turbine land, we would often say, let's set this machine 10 thousandths low and 2 open at the top, because the turbine itself doesn't grow straight up and down. Say an air compressor might go straight up, so they would say, take the whole air compressor and leave it 10 low. If that's the case, you just do the feet. But if you have a machine that's going to grow more in the back than in the front, it's easier to be done at the coupling, because the length of the machine matters. So there are 2 different ways to handle it. We can do both. We can do it as a thermal growth number or a target value at the coupling. Okay, so it's a target at the coupling, thermal growth at the feet. Again, we're trying to figure out where this thing lives while it's running. Okay, this is a picture of our calculator, and I think all of our tools have this calculator built in. A lot of people don't know that it's in there, but it is. And you can select thermal growth, and you can go into this calculator. You can select the material that it's made of, the temperature that you're performing the alignment at, and the final temperature that it runs at, okay, and the height of the shaft. And it will give you the actual thermal expansion of that material at that temperature. And you can calculate where you think it's going to live. It's a nice attempt. It gets you pretty close, okay? I can tell you this, the most accurate way to perform thermal growth is to watch it live time, okay? But we can calculate it. And I tell people to do this if you have 2 machines that are a really different temperature. If I have a motor that runs at a certain temperature and the pump is over there running about the same temperature, that's a wash. You can just align it true. But if one runs really cold and one runs really hot, it might be worthwhile to look at those temperatures and use this calculator to try to figure out where stuff lives, okay? So thermal growth done at the coupling looks like this, okay? We don't have a calculator here, but you can simply put in the numbers for whether or not you want the coupling open at the top or low on the left or the right. And we can do it for horizontal as well, okay? Now, Calculated lets you use the calculator. That's the one I just showed you, right? But if you look at this bottom picture, and this is a little hard to see, but if you'll notice, there's a laser and a sensor in that picture on that machine down there with a coupling guard on it, okay? And they're mounted right on the housings of the machine. So we mount them on the housing, we put the coupling cover on, we line it up cold, and then we turn the machine on and watch it run. It is an amazing answer to where does my machine live? And I think more people should be performing this process, because it is a really easy thing to do, and it gives an eye-opening result sometimes. So you'll get your results in a graph form, and the graph will tell you both your vertical offset and vertical angularity, and if there was any horizontal offsets, you'll see those as well. And all these numbers come out, you find out exactly where your machine is living. You can open valves, close valves, speed it up, slow it down, run it in the summer, in the winter, and really find out where your machinery lives. When we line things up, we often do such a great job. We line something up within 1/1000th of an inch because we think we're awesome. Well, turns out hardly anything lives right where it is when it's cold. Hardly anything. And after doing a few of these thermal growth live trend studies, I figured, wow, we're really shooting for a small tolerance, yet the machine doesn't live there. So let's find out where it lives, and let's line it up so that it grows into position, and it is a game changer. I tell people, if they have a machine that's giving them trouble, do this. This thermal growth study is a really, really beneficial process, okay? So we'll talk about tolerances for a minute, and I mentioned that because if you look at this table, these are the tolerances that are built right into our tools. The way this table works, the RPMs determines the tolerance. Now, we're in the grayed out area because I'm in thousandths. I don't know how many people use millimeters, but I'm a thousandths of an inch guy. If you look at this chart, at 1800 RPMs, in order to get okay, your offset, that's this center line to center line measurement. To get okay, you need to be within 3000ths. To get the smiley face, and let's just shoot for smiley faces, that's what most people do, you need to be within 2000ths, okay? But if you go down to, excuse me, 3600 RPMs, you need to be within 1. Getting an alignment on a large machine within 1/1000th of an inch is really not that easy to do. 1/1000th is a really small number. I mean, one of your hairs on your head is about 3/1000ths, sometimes 4. So 1/3 of the size of a hair is how precise we're trying to line things up. It's amazing. We can do it relatively easy now with these lasers. It's amazing, super simple to do. However, the machine doesn't often live there. When you heat it up and you run it, it goes somewhere different. And until we know where that is, we don't really have precision alignment, okay? This tolerance table gives us, you get a different angularity. You're allowed to have a little bit more misalignment, so the tolerances are different for angularity than our offset. Sometimes I'll go a place and they'll say, we line everything within 2. Yeah, that's fine, but sometimes you don't need to. If it's a slower moving machine, we give you more tolerance. And the other thing about spacer shafts, if you look down here, is the tolerance is per inch of spacer. So if you have a really long spacer, our tool gives you a lot of tolerance. So it's nice to have that spacer option built into the tool, okay? So I like to show that the RPMs are the tolerances are dependent on the RPMs. The faster it spins, the tighter the tolerance, and that obviously just makes sense, okay? If it's gonna run really fast, we wanna have a really tight tolerance, okay? I like to show this picture because I was in a steel place, right? And here's the other one. I was in a steel place and this guy said to me, where did you get that tolerance table? Why are they so tight? He had me come in and he had me measure all of the machines in his, in a row. There had to be, I don't know, 15 or 20 machines. And he goes, I just want an alignment check. I want to know where I'm at, because he had coupling failures. So I went in through and I lined it. Absolutely nothing was in tolerance, nothing. And I gave him all the results. I said, you're way out of tolerance. He goes, well, where did you get those tolerances? Why do you have such tight numbers? And at the time, there wasn't an ANSI standard. These were numbers that our founder came up with his vibration people. And these numbers have been built into the Rotoline since I started in the 80s. So these are very reliable numbers. And if you get your machinery to within these tolerances, you're going to be fine. Apparently, his equipment looked like this. He literally wore out the inside of that coupling, decided he couldn't live without that machine, and so he welded the hub to the cover, and he kept running the machine. And he had several of these where they were just, couplings were just exploded. Okay, so he argued with me that my tolerances were too tight, and I argued with him he had the worst running machines I'd ever come across. So I love to show those pictures, and like I said earlier, if you have pictures of failures, send them to me because I think it's fun to look at them. I like to tell people that maybe you have a reason. Okay. In that case, I remembered saying to him, I don't have a standard that the American National Standards Institute gave me. I only have the ones that our company put into the tool. Turns out, short time later, ANSI put out a bunch of standards, and they look like this. Again, they are RPM dependent. Okay, so, and I don't need to read you the exact numbers, but if the RPMs are higher, the tolerance should be tighter. And there's different grades of tolerances, but you need to align your machines better if they run faster. Our tool has the ANSI standards built right in. You can select them. Ours are very close to the highest one, the grade 1, I believe, or whatever, the highest grade one. So standards are important, or tolerances are important. You're going to want to line things up to the best tolerance that you can find. Okay. Now we're going to talk about why we're here. Okay. And the original title was the importance of alignment. Okay. And the real reason we perform alignment is we want our machinery to run better, right? We want a return on investment. The return on investment has to do with, why did I buy a laser in the first place? Okay. And there are a lot of reasons. I'm going to talk about the real reasons because the tool itself can pay for itself. Our tool is a really easy tool to learn how to use, and anybody with a maintenance force should, I want to say almost definitely, if they have anything that rotates, should definitely have one in their toolkit or tool room, I would say. But the return on investment for this tool, and it seems very expensive, but you can, as I'll show you in a second, it's real easy to explain why I would want to justify purchasing a really good tool for laser alignment. Okay, in this case, they're talking about electric usage. There are plenty of people who have done studies on how well things run when they're lined up perfectly and how much electric they use. And then there's other studies on repairs, and what this particular picture just says seal replacement costs. Okay, because I was in the nuclear world, so seal replacement costs were a big deal. And when we started running things more aligned, we ran at a much better seal life. Okay. So first we'll talk about bearing life cycle, and again, I don't have the exact person who gave me these numbers, but I think these studies were done by our people, and I can't argue with them really, because I'm not going to give you these are in euros. I guess I could have translated them to dollars, but I think it's important more to know the percentage of life expectancy you get as opposed to how many dollars you're going to actually save, because each thing would be, machine specific, right? But bearing life cycle, bearing repair costs, okay, are very high, and obviously things are getting more expensive today. I mean, maybe way worse than they've ever been, right? But the life cycle of a normal bearing, okay, with good alignment, this chart shows, and this is in millimeters, I apologize, I'm a thousandths of an inch guy, but if your alignment, okay, if your offset is at 0.25 millimeters, you get a pretty much 90% life out of your bearing, okay? And in just a very small difference in alignment up to 1 millimeter, the life in the bearing loss of life is about 50% of its real honest to goodness life. And that's a pretty huge problem, because bearings being expensive, not even talking about your loss of machinery use, but bearings 50% longer with good alignment. Okay, so these guys over here, they used an actual number of offset. Their offset being 0.2 millimeters. The additional cost of bearings per year is 35 euro. But if you get down to 0.75 millimeters, we're at 124. And I'm going to just talk about the ratio. I know it's not in dollars and cents, but apologize for that. I didn't want to convert it because I couldn't change these pictures. I'm not a computer guy. I'm a nuts and bolts guy. So with a little bit of misalignment, you see a lot less bearing life. So bearing life, number one, 50% worse with poor alignment. Okay. The next one we'll talk about is mechanical seal repairs and reduction in seal repairs with good alignment. And this is over 4 years, this particular study was done. And I'm just talking about the value of these things. The actual numbers or the actual percentages, not really necessary to be argued, but it's good to understand that reduction in seal repairs over 4 years was down 65% with good alignment. Okay, so these people come up with some costs for the seals, but again, this would compare to maybe one small pump case. The one I showed you earlier, which was a simple motor and a simple pump. Okay, and that particular picture was the type of machine they did these studies on. But 51 euros compared to 235, that's a pretty big deal. Okay, and we're only just talking about the seal repairs. The cost of a seal repair often goes way beyond, because you pull a seal apart, sometimes you're going into the whole pump. If I pull a pump apart just to replace a seal, often I'm in a total rebuild, which is way more expensive than just the seal repair. But for this case, we're going to just talk about the seals. Okay, and then we're going to talk about pump repairs in general. So bearings, 50% life. Seals, 65% life. And this just says pump repairs. Okay, so they're going to give you just a 30% drop in pump repairs with good alignment. Okay, so pump repairs could be incredibly expensive. Wear rings, bearings, oil seals, grease problems, things like cavitation are maybe speed specific, but good alignment definitely gives you less repair prices. Okay, so pump repairs, they're looking at 145 euros if you have 0.2 millimeter offset, and if you are up at 0.75, we're at 670. That's a pretty big increase in pump repairs. Now, all these things consider just the repair of that machine. Okay. We didn't get the pump. Let's go to power consumption. But so the fourth thing, we talk about general pump repairs, seals, bearings. Okay, and then the last one is a really interesting one that most people don't really measure is power consumption. So this picture has the total, and I think the next slide shows us the total, but power consumption will be down 10% with good alignment. I didn't realize that, but I did have a customer tell me one time that after their alignment process was instilled into their place, they had a really, really large decrease in power usage. And he even told me what the number was. I don't know what it was, but it was very large. And the amount of power usage that they got savings, okay, was obvious to them. And they showed this maintenance manager the results. And he said, I just performed all these alignments, got you better power usage, power savings. He goes, I want that money in my budget. And they actually gave him some. They said, no, now you have more money in your budget because of the savings just in power alone. That's disregarding the bearings and the seals and the pump repairs. So they were able to prove that putting an alignment system into use, okay, saved the company a lot of money in power consumption. Right? So they're saying 10%. 10% is a pretty big number. And I'll tell you why it's a big number, because where am I at now? This picture here shows you the life cycle costs of the pump entirely. So I buy a pump. What does that pump cost me? I buy it, and 5% of its entire cost, okay, is the purchase price. I buy a pump, I don't know what it costs, $10,000, okay? Of its entire life, that's only 5% of all the money I spent on that pump. The next 8% is maintenance costs, just keeping it running. So if I have to spend 8% after the 5% of its total costs on maintenance, that's understandable. But the real cost of that pump is the power that it consumes. So if I have a pump and over the cost of its entire life, this is the entire life, 80% of what I spent on that pump happens to be in how much power it uses. 10% is a pretty big deal, right? So I try to sell these. I used to have a territory to sell these, and I would, walk into a place and they'd say, boy, that's a lot of money for a tool like that. And if you really can get down to brass tacks and say, this is what really costs you in your machinery, buying one of these tools is a easily recoverable cost. So the real return on your investment is all these things: power consumption, bearings, repairs, seals, okay? And those things don't even include the downtime, okay? So the real big one, and it was easy being in a nuclear power plant to say we need good running equipment. It's real easy to say that. And the reason we said that there was when the plant came down, it lost $1.25 million, $1.25 million a day, dollars per day. And if the plant came off for a pump that went bad, it took 2 days to bring it back to full power, to turn it back on again. You don't just flip a switch. It takes you 2 full days to get the plant to come back up again. So one pump failure, okay, was $2.5 million. And those numbers don't even get counted in to these other problems. How much did it cost the pump to repair? How much did it cost for the seals? How much did the bearings cost? If you have a failure that brings your plant down, your process is ended. So the real cost of your machinery running well is far beyond all these repair costs. Now I get it, sometimes you'll have a backup, but if one of these machines brings your power plant off, or your whatever plant you're running, if it brings it off, you're losing a lot of money, right? So the return on investment to have good precision alignment is right there, okay? Often these numbers can't be proven. You can't put them on a piece of paper. You can't say, okay, we bought this $31,000 tool and it saved us this much, because the savings are hidden. You got a plant that runs well, okay? And you have to do a lot of math to figure out what the real return on investment is, okay? But
David,
one,
there.
excuse me?
We lost you for just a second.
Oh, I'm sorry. I hope I'm still here.
Yep, you're all good again.
Okay, so just total cost, and somebody did these calculations. Like I said, this is hard to put to any specific machine, but for this particular pump setup, the one we showed earlier, 165 euros if it runs at 0.05 offset, 441 euros if it, and I apologize for these not being dollars, but I didn't want to do the math, and 1,624 annual costs, 1 year, each year, with poor alignment. Okay, so those are pretty big numbers, right? For each machine you have running. Obviously, this is just for this one machine, but the comparison is very similar, probably to most machines. Okay, so here's some math for you, I guess. Somebody says with 50, 75 kilowatt pumps, your annual cost can ascend to 22,000 and can be reduced by 80 to 50. Right, so these numbers, like I said, these numbers won't be exact for any of your equipment really, but the percentage is what we care about, okay? We really care about what percentage of costs are we really gonna waste by not having a good alignment program, okay? So the life cycle cost of a pump, big picture there. It's kind of hard to understand that most of your money goes into power, but we're gonna save some by doing good alignments, and maintenance and purchase costs you're not gonna change, okay? So significant power savings and benefits by alignment, far less repairs, okay, seal reduction repairs, bearing life cycle is obviously 50% is a huge problem with bearings going bad, right? And a reduction in power. So those are the real benefits promised by laser alignment. And we've done a lot of studies and seen these things happen. Personally, I have experience with watching things run better when they're aligned better, just from the very get-go with a very low vibration and maybe very low heat. Those two things are immediately obvious if you start performing good alignments, okay? So reduced cost of spare parts, mechanical seals, labor costs, brackets, documentation issues, and power consumption at the plant, right? Increased life cycle of the operating machines. Again, plant availability is something I can't calculate, but if you have a plant that makes a lot of money, why not keep making money, okay? Reliability, safety is another thing. Obviously, if things are gonna blow up, bad couplings. You saw that picture of the coupling of that thing. It was spinning. It probably could have exploded and shrapnel through the plant. But and everybody cares about a cleaner environment with lower use, right? Okay, so I made it all the way to thank you. I think I hit the time pretty well. I know we were slated for an hour. I got a couple minutes left. If you have questions, I think there is a way. She says there's a way for you to get some in. And if they have any and then she can get them to me, I'll be glad to answer them.
Great. Well, David, we do have a few questions and we have about 3 minutes left. Can we answer a few of the questions that came in?
Sure, I'd be glad to. You have to try to speak clearer. You sound a little fuzzy for some reason, but.
Oh, I'm sorry. I don't know what's going on with the audio today. Let's see. The first one was, why is it important to consider thermal growth?
Okay, so that and I tried to make it clear, but thermal growth, it relates to where the machine runs, where the machine lives when it's running. So if I align something when it's cold and it's sitting still, and I do a perfect job and I get it within 1/1000th of an inch, and I turn it on, and one machine grows a lot. I've seen steam turbines grow 90 thousandths. I had this one really hot. It ran at 700 degrees, but it grew 90 thousandths, and we had to purposely offset the machine when it was cold so that when it grew into place, it ran aligned. So it's almost obvious to me, if one thing grows and the other one doesn't, when it's running, it will be misaligned, even though you think you did a great job when it was cold. And I hope that explains it, but thermal growth is the aligner's, I don't want to say nightmare, but it should be his target all the time.
All right, thank you. We have about a dozen questions, but I'm going to try to slip 2 more in before we have to wrap up.
Okay.
The next question is there any relationship between motor current drawn and alignment?
Motor current, what? I'm sorry.
That's all right. Is there any relationship between motor current drawn and alignment?
Oh, yeah. So those last few slides I showed you had to do with power savings, and I think power consumption, where are we at? So power consumption, if the alignment, you see there's a little chart here. If you look at this chart at 0.25 millimeters offset, okay, we have very little change in power consumption. But if you get up above a millimeter of misalignment, the power usage was 10% greater. So the reduction in power consumption, meaning line current, right? Hopefully, if that's their question, is really affected by poor alignment. Okay, so and they've done these measurements. It's a pretty easy thing to do. You could probably just take some current readings and then perform an alignment and see if your current readings got better. So that should be pretty easy. The answer is yes. And that's a big deal because it's over the cost of the pump. That's a big savings.
All right, thank you, David. I have one more question that I'm going to sneak in really quickly because I think it's important for everyone. There's a question, is training available through Fluke for the use of alignment tools?
Absolutely. So we have a we have a service department that handles training. We offer it in two different ways. We have a facility in Bonita Springs, Florida, where around quarterly we do what we call it a boot camp. It's an alignment boot camp, and it's 2 days of training. And I don't have the prices on me, but it's on our website, I believe. You get 2 days of alignment training. It is it 100% covers almost everything you would need to know to use one of our tools. The other option would be to have one of our trainers come out to your facility and teach your people. It's a little harder that way because we have to bring a bunch of these little trainers and we set them up so that everybody gets a little hands-on. But yeah, we will travel to your plant with a trainer and a bunch of little simulators, I call it, for alignment, and we teach the tool soup to nuts from the get-go right through all the options that are built in. Okay, I think typically if you buy one new, you'll have your sales guy come out and show you how to do it, but the training is also available through us.
All right. Well, thank you, David, for an amazing presentation. I know many of you had questions that we didn't get to. Tomorrow you will get a thank you email for joining this webinar. Please feel free to respond to that with your questions. I'll make sure that I get those to David for responses. To the audience, thank you so much for joining us today. As a quick FYI, when you exit GoToWebinar, there will be a window that pops up with a very short 30-second survey. We would appreciate your feedback on today's session. Thank you for joining today, and I'll close the webinar now. David, thank you so much.
Okay, thank you all.